Hey, Chad. Hey, Struggle Bear 022. Hey, Giselle. Oh, Giselle. All right. So, hey, Thick. Hey, Ashley. Okay. So, as you guys can see, I have muted me so that I don't hear any feedback. Okay, because sometimes that feedback is real. Okay. So let me go ahead and get me on over here so I can switch the screen. Okay. So here we go. All right. So now, as you guys can see, for those of you all that want to go back and listen to the videos for later, you can on my other channel. And while we're talking about that too, in case some of you guys need to know what channel I am on this right here, just in case you guys missed it. So let me go ahead and pull it up so that you guys can be aware of my contact info. Okay. So here it is right here. Well, I thought it was up here. Okay, here we go. So that is my channel right there. So if you guys are wanting to go to my YouTube channel, you can. And if you want to do a love offering, you can do that as well. I do free chemistry tutoring Monday through Thursday at 12 noon Eastern Standard Time. I also go live now that April is here. I am going live also in the evening times, Monday through Thursday at 7 p.m. Eastern Standard Time. So for those of you guys that need some extra chemistry help, this is how you can find me, okay? Monday through Thursday. Matter of fact, let me put that down here too, so that way you guys get it. Monday through Thursday, okay? 12 noon and 7 p.m. Eastern Standard Time. So for those of you guys that need extra help, these are the times that I'm giving away the free stuff. However, if you want one-on-one attention, by all means, hit the link in my bio and I got you, okay? I got you. So now we're going to go ahead and get started on the lesson. Someone wanted to know how to do Hess's Law. So let me go ahead and pull up some of my prior notes on Hess's Law, because this is something that we actually covered a few weeks ago, but I don't mind going back because that's what you guys want to know. So this is what I'm doing, this information for you guys, okay? So let me see. It's going to take me a second to pull it up, but just bear with me, okay? Because I got you. I got you on what you want to know. We actually did this last week also, okay? So to the young lady that wanted to know about Hess's Law, is there anything specific that you want me to cover on that particular topic? I know also with enthalpy, that's something else that we kind of went over too. So is there anything in particular that you're looking for when it comes to this information? If so, let me know. Put that down in the chat box also, so I can have that information for you too. I'm just pulling up all of my old notes from a couple of weeks ago. Actually, it was just last week as we're speaking. Last week. Okay, so let me go ahead and kind of just address some of those concerns, okay? So here's the thing. When it comes to heat of formation, Hess's Law, what you're having to do is something that's quite simple, okay? So as you can see, I worked out several of these problems previously, okay? I worked out several of them previously, but let me kind of get you through one of those examples so you can kind of see how simple Hess's Law can actually be, okay? So what I've got here for you is a chart, okay? One of the things that you have to know about Hess's Law deals with a chart that you have to use whenever you're dealing with the heats of formation for the given chemical reaction. So for instance, if I look at this one example right here, okay? And this one was lengthy. Let me go to one that was a little shorter so you can get straight to the answer. Okay, this is one right here, okay? So right here on the screen, it says calculate the heat of reaction for the decomposition of hydrogen peroxide that decomposes to water and oxygen gas. And what you have to do is use the table of heats of formation for those given values. What you need to know is that the water, the hydrogen peroxide, for hydrogen peroxide, the heat of formation was negative 187.8. The heat of formation for water was negative 285.8. And then for oxygen, it was set at 0. Something else you need to know is that you also need to make sure that your equation is balanced, because if it's not balanced, then your answers are going to become wrong, okay? So if you don't remember, the heat of formation is basically your products minus your reactants. So whenever you are doing your equations, such as what you see here on the screen, okay, you'll notice how I first put down underneath each of them. Okay, these are the values from that chart that I just showed you, right? But then I went through and I rewrote the chemical reaction here, and I also wrote the numbers for each of these formulas underneath them. So as you can see right here, matter of fact, let me kind of take some things off so you can see this. So I know the heat of formation for hydrogen peroxide was negative 187.8 kilojoules per mole. So I multiplied that times 2, and that's how I got negative 375.6 kilojoules per mole. That's equal to 2 times the heat of formation for water, which was negative 285.8 kilojoules per mole. Of course, oxygen was set to 0. So when I multiplied 2 times the negative 285.8 kilojoules per mole, I ended up with negative 571.6. Now, here is the other thing too. When you're doing heats of formation, okay, and remember the formula is the reactants minus the products, you're going to have to take your reactants here, this left side, and bring it over to the right side. And that's why the sign changed to a positive 375. And when you do that, okay, because I'm bringing the 375 to the other side, I'm going to cancel out this side because we no longer need that. And all I'm going to do now is combine these two together. So I'm technically adding them. But because the 285 was negative, when I multiplied it times the 2, negative 571.6 plus 375.6, gave us the negative 196 kilojoules per mole, okay? So again, when it comes to Hess's law, all you're doing is remembering the rules, okay? You got to remember the rules. And let me also kind of recap something else for you too. If you are switching numbers around, for instance, like this one that I did before, if you are switching the chemical formulas around to have it set up the way you want it to look, you're going to also have to change the sign. So if the sign was initially negative, but you're switching the chemical reaction around, it's going to now become positive, okay? It's going to become positive. So that's the thing you have to remember when it comes to these chemical reactions with Hess's law. The delta H will change in terms of the sign, and the chemical reaction must be balanced. So there are several things you have to keep in mind when you're doing these types of problems, okay? Jaded Blaze, so do you have any specific questions, or did that answer your question? Now, here's something else. Here's another example that I did right here. Also, in terms of calculating the delta H. Okay, excellent. And remember, Jaded Blaze, if you want to go back and look at some of these problems, I have them up on my YouTube channel from last week. Okay, so and if you want to go back and look at these again, it's titled thermodynamics. Okay, so you can always go back to look at this to make sure. And I'm going to recap this one as well. If they're wanting you to calculate the delta H for the following reactions, again, you got to look at that chart, that table that I gave you or that I showed you at the very beginning. And that table is going to give you these numbers here that are written in red. So I'm giving you the heat of formation for calcium carbonate, calcium oxide, and carbon dioxide. Okay. Now, what I also did with this, Oh, you're welcome, honey. You're welcome. What I also did with this particular problem is I made sure to put the numbers underneath each formula, okay, in terms of their heats of formation, whatever they gave me. But something else I want to make sure that you know how to do is that you take care of each side that has numbers that you're adding together. So for instance, I know that the heat of formation for calcium carbonate was negative 1207. So I put that underneath calcium carbonate. Over here, calcium oxide was 634.9 and carbon dioxide was negative 393.5. This equation was already balanced, so I did not have to do that. I know, William. William. And so then, because these two are together, the negative 634.9 and the minus 393.5, I'm going to do that operation first. Now, you know, when you have two negatives, you're going to keep the negative sign there, okay? So now, oh, okay, I got you. I got you. Yes, by all means, make sure. That's okay, William. That is okay. Your presence is the present. Okay, your presence is the present. So if those of you guys that are taking chemistry this summer, make sure you come back and holler at me because I'm going to make sure that you do well this summer. Okay, I want to make sure that you guys do well this summer because chemistry during the summertime is a force to be reckoned with. It's doable, but you've got to be committed to it. Okay, laugh my ass off. Said honestly, Chem 1 and 2 is math and memorization. Yeah, it is a lot of math and memorization in terms of those formulas and those rules. And yes, I totally would agree with you on that. Yes. And so to finish this problem off, excuse me, guys, to finish this problem off, all you would have to do, again, when you do the negative 634.9 minus the negative 393.5, you get negative 1028.4. Remember, I'm going to bring the reactants over here to this side. That's why I was crossing this out, okay? To make sure I cancel out the negative 1207 with the positive 1207, okay? And then you end up with the answer of 179.2 kilojoules per mole. Now, on yesterday, we did talk about gas laws. And so that's where our lesson went. Normally, I would address this particular question that someone had, that Jaded Blaze had. I would have addressed this problem at the end, but I went on ahead and got it answered for her because I wanted to make sure that that they could get what they needed to get answered right away. Okay. So now what I'm going to do is go through my unit on the gas laws, okay? So let me go ahead and back out of this for a second. Let me go ahead and clear everything off, okay? And let me go back. Yes, y'all see me right here. Let me go back to my gas laws, okay? So yesterday, when we were talking about the gas laws, we did discuss Charles and Boyle's law, okay? And what we had to do and realize is that when you're looking at these gas laws, you've got to keep in mind the different units, okay? The different units. I know, and Callie, you're going to do fine, okay, Callie? You're going to do very well on your exam, okay? Just continue to practice and study what you know and the things that you're confused about. Make sure that you make notes of them. I've been telling students to make note cards. And I call this note card chemistry because you can write down quick formulas that you need for, let's say, acids and bases, or the rules for writing chemical reactions, or the rules for formulas, or the rules for Hess's law, enthalpy, all of that. If you just write down those rules just on each individual note card, when you're just, standing around not doing anything, you can just pull your note cards out. Sometimes it's the little things that you do to make a big difference. And I always say less is more. Less is more. Yes, LMAO, you're right. Organic chemistry does expect you to know a lot of things beforehand. You're absolutely right about that. Now, what I'm going to do as I go through these rules with you all, the gas law, we know that with Boyle's law, so let me scroll down here. Boyle's law, okay, deals with pressure and volume. And just to recap, they are inversely proportional to each other. So that means if one goes up, the other one will go down, okay? And the typical graph for Boyle's law is a curve, okay? When you're talking about Boyle's law, because again, it's dealing with pressure. And let me write this here. Boyle's law deals with pressure and volume where your temperature remains constant, okay? And again, the graph typically looks like a little curve there, all right? Now, something else and let me be more specific, pressure and volume, okay? Now, something else that we talked about yesterday dealt with Charles' law, okay? And Charles' law deals with temperature and volume, right here, temperature and volume. And what you needed to know is that as one goes up, the other one goes down. I'm sorry, they both go up at the same time and they both go down at the same time. So if the temperature goes up, the volume is going to go up. If the temperature drops, the volume is going to drop. And that's because they are directly related to each other. So your graph will have a straight line in this particular case. Also, pressure would remain constant, okay, in this particular instance here. Your temperature also must be in Kelvin. So that means if I have the temperature is degrees Celsius right here, okay, you would need to make sure that in order to get your Kelvin, it's degrees Celsius plus 273, okay? That is what you have to remember when it comes to Charles' law. Now, the other law that we're going to actually get into today, because we did several problems with this yesterday. The other problem that we're going to get into today deals with gay-Lussac's law, okay? So let me go ahead and pull up gay-Lussac's law so that you'll know exactly what to do, okay? Gay-Lussac's law tells you that your pressure and temperature are also directly related to each other, okay? They are also directly related to each other, and your temperature must be in Kelvin. Your temperature must be in Kelvin. And because your temperature must be in Kelvin, that means that whenever you're given the numbers in degrees Celsius, you've got to convert that by just simply adding 273 to that value. So remember, as your pressure increases, your temperature increases. If your pressure decreases, your temperature will decrease. The moles and volume will remain constant. So these are the two variables here that will remain constant when you talk about gay-Lussac's law, okay? So your pressure and temperature, because they are directly related to each other, you're going to have a straight line, okay? A straight line. So I do have a few problems that we can do, that we can work on, just to make sure that you guys are good to go when it comes to this particular part of our lesson, okay? So here it tells you that an aerosol can be dangerous if they are heated because they explode. Now, you know, an aerosol can is basically spraying out, a liquid form that's gaseous in the can, but it comes out in liquid form. Now, if you have a container of hairspray with a pressure of 4.0 atms at a room temperature of 25 degrees, if you throw that in a fire, what do you think is going to happen? Well, let's talk about it, okay? Let's talk about it. Matter of fact, let me highlight some of these numbers for you, okay? So you have 4.0 atm. That's the first pressure reading. That's why I wrote 4.0 atms. The room temperature reading was 25 degrees Celsius. I wrote that there. But you've got to add, of course, 273 to that to get it into Kelvin. That's where the 298 comes from. And now it says if the temperature of the gas inside the aerosol can reaches 402 degrees Celsius, what will the pressure be? The aerosol container may explode if the pressure exceeds 8.0 ATM. Okay, so now here's what I'm going to do, just so you guys can see this here. We're going to actually figure out what the pressure will be, okay? Because that's what they're asking. So I'm going to actually erase this one for right now because I want to come back to that, okay? And what I'm going to show you here is that in the first problem, it says if the temperature of the gas inside the aerosol can reaches 402 degrees, what will be the pressure, okay? So again, they gave you 402 degrees Celsius. Again, you've got to add 273 to that. And you get 675 Kelvin, okay? Add it. I'm going to let you go back and watch my videos. I'm on YouTube on Learn Chemistry with Professor TK the Chemist, and you can hit the link in my bio so that you can go back and re-look at this at your leisure, okay? But you're not going to fail your exam. You got to think positive. As long as you've been doing what you're supposed to do, you should be good to go. Okay, so now what you're going to do for P2, because that's what they're asking you about. In this question right here, it says, what will its pressure become? Okay, so we have to go back and look at the formula to find P2. Now remember, this is your base formula right here. P1 times T2 equals P2 times T1. So that's our formula that we're going to use right there, okay? We're going to use that one. So I'm going to write it here so that you guys can see that, okay? So again, the formula is P1 times T2 equals P2 times T1. Now, excuse me. Remember, we're looking for P2. So notice I'm isolating that one and covering it up because what I'm going to do is divide both sides by T1. T as in terrific, T1. So I'm going to get rid of that, and I'm left with P2 by itself right here, as you guys can see. And so now my formula that I'm looking for P2, okay, is equal to P1 times T2 over T1. Now, all I need to do is plug those numbers in, okay? Plug those numbers in. And let's do that as well to make sure that we're good to go. Okay, I'm just scooting that one down. Hold on, let me go back. Okay, so since I know that this is my formula here, okay, I'm going to plug in those values again. P1 times T2 over T1. So the first pressure reading, before we give you the answer though, in terms of solving this, let's figure out what our pressure could potentially be now or become. So if you notice here, your temperature went from 298 to 675. So our temperature increased. You can basically say that our temperature literally doubled, okay? It literally doubled. It basically went from 300 to, let's say, 600, okay? If we're trying to guesstimate, or 700, if we're trying to guesstimate, we can kind of predict that our answer has doubled. So if our temperature has doubled, that means our pressure is going to also increase, and it's also going to double, okay? Or come close to it, okay? So now, what I'm going to do, okay, is plug in the P1, which again was 4.0 ATMs, okay? 4.0 ATM times T2. That was the second temperature reading was 675 Kelvin. And the first temperature reading was 298 Kelvin, okay? Those are the values here above. So now all I'm going to do is take my calculator and plug that in. I've got 4.0 times 675 divided by 298. And I get 9, okay? You need two significant digits, so we'll say 9.1. All right? So P2 is equal to 9.1 ATM. And again, we cancel out our kelvins, okay, because we don't need that. And here's your answer right here, 9.1 ATM. Now, if we go back to the question, though, it says the aerosol can may explode if the pressure inside. Let me zoom in so y'all can see that. Okay, it says the aerosol can may explode if the pressure inside exceeds 8.0 ATM. Okay, right there. So my question is, will this can explode based on the calculated results? And the answer is yes, because it says it'll explode if the pressure if it exceeds 8.1. And in this case, it exceeded it. So yes, this can will explode. Okay, now we're going to do the next problem, okay? And y'all, when it comes to these problems, you've got to read what they're telling you, okay? You got to read what they're telling you. Thank you guys so much for sharing the lives and following me. I appreciate that. Thank you, Steph and Samantha. Thank you, Fatima. And to everyone that I may have missed, I appreciate you guys. Now, what you want to do, when we talked about this lesson yesterday, we discussed how when you're dealing with these problems, okay, you've got to make sure that you follow and read each problem to solve for what they're telling you. So in this particular example here, it says solve for the new pressure in millimeters of mercury. We're still dealing with gay-Lussac's law, which deals with pressure and temperature. Now, in this problem, they said that the initial pressure of 1200 torr at 155 degrees Celsius is cooled to 0 degrees Celsius. They want you to calculate the new pressure. All right, here we go with the things that we have to plug in. They told you the initial pressure was 1200 torr. They also told you that the initial temperature was 155 degrees Celsius. But remember, you've got to put your answer in Kelvin. So we're going to add 273 to that number. And we get 428 Kelvin. It said it cooled to 0 degrees Celsius. Again, just add 273 to that. Ooh, I wrote the numbers backwards. 273 to that. And you get 273. Now, they want to know the pressure, but get this, in millimeters of mercury. All right, so here's what you're going to do first. Solve the problem the normal way, okay? We're solving for P2. So if you don't remember what the formula for P2 was, let's just go ahead. I'm going to write it down so you all can remember, okay? P2 is equal to P1 times T2 over T1. Now, before we go through the formula, let's evaluate the numbers of what we already know. Initially, the temperature was 428, but then it dropped. It decreased to 273. So let's just kind of guesstimate and say that our temperature kind of dropped by half, okay? So if it decreased by half, approximately, okay, again, I'm saying approximately, then what is your pressure doing? Your pressure is also going to drop by close to a half. So I know that my pressure that we're looking for in torr is going to be less than 1200, of course. Okay. So I'm guesstimating it's going to be close to like 600. But remember, even though we're saying torr, they want the final answer in millimeters of mercury. Right here. If you see on the board, they want the answer in millimeters of mercury. So what do I have to do? We're going to first solve it for P2, get that answer in torr, and then convert the answer to millimeters of mercury. And how do we do that? Here's my conversion factor right here. 1 ATM equals 760 torr, which also equals 760 millimeters of mercury. Okay? So here we go. P2 equals, so P1 was 1200 torr. T2 was 273 Kelvin. T1 was 428 Kelvin. All right, let's get rid of the Ks because we don't need them anymore, but let's plug in what we know, okay? We got 1200 times 273 divided by 428, and we get 765, okay? So my P2 is 765 torr, okay? So I told you it was going to come close to, 600 when we guesstimated it, okay? That was just a rough guesstimation, not an actual factual, but a rough guesstimation. So now, here's what we've got to do. They want the answer in millimeters of mercury. You see that? So what am I going to do? I'm going to convert, okay? I'm going to convert. So I'm going to take that 765 torr times, remember, they want the answer in millimeters of mercury. I know that 760 torr is on the bottom, okay? Because remember, right here, 760 torr equals also 760 millimeters of mercury. And it just so happens to y'all that these two cancel out, okay? Well, the torrs cancel out, yes, but also the numbers themselves because they're the same on the top and the bottom. So our answer becomes 765 millimeters of mercury. Okay, that's our answer right there. Any questions from anybody before we go to the next problem? Again, guys, all you have to remember is that whatever you're given in the problem, you can guesstimate the answer by knowing what has happened with each variable. If they both go up, then, for instance, if the pressure goes up, then you know your temperature is going to go up. If your pressure drops, then you know your temperature is going to drop. Okay? Okay, good question, K2. Why is the torr in the bottom of the fraction 760 and not 765? Because remember, this was the calculated answer that we got right here. This P2 that you see me highlighting in purple, that was the calculated result. So we've got to convert that number, 765, now we got to convert that to millimeters of mercury per the question that was given, okay? So we have to convert 765 torr to millimeters of mercury. And remember, let me go back up here so you can see this. I'm gonna have to change the screen so you can see. This chart right here, I'm gonna zoom in so you can see that chart. This chart is your conversion chart whenever you're trying to convert an ATM to a millimeters of mercury or to a torr or kilopascals or to pounds per square inch. You have to use these conversions right here. They're all equal to one another essentially. So when you're converting, whatever you're trying to get to, okay, like in this example here on the bottom, if I want to convert ATM to a torr, I've got to put the corresponding conversion factor on the bottom so that the units can cancel out. So the ATM's canceled out, but what I'm trying to convert to should go on the bottom, which in this case is a torr. So the torr is on the top. And that's how we were able to get our final answer for that one example right here. So if we go back to the example that you're asking about, okay, just FYI. Okay, you're welcome. You're welcome. Because our result initially ended up being 765 torr, we have to convert that to millimeters of mercury. And if you see right here, it says solve for the new pressure in millimeters of mercury. So that's what I did right here. I used my conversion factor. My conversion factor said 760 torr is equal to millimeters of mercury, is equal to 1 atm, is equal to 14.7 pounds per square inch. But I only needed to use these two right here that I'm going to highlight. I only need to use those two. So therefore, what I needed to get to, which was a 760 millimeters of mercury, that number went on top. What I need to get rid of was the 760 torr. And then the torrs canceled out. And ironically, the numbers also canceled out. And this is what our final result is: 765 millimeters of mercury. Now, we've got another problem right here, okay? Notice how, oh, wait, let me see. Oh, we didn't do letter B. My bad. We didn't do letter B. So let's do letter B now. Different problem, but they still want you to put the answer in millimeters of mercury because this time you have an ATM, okay? So, excuse me. Let's go ahead and put this one down here now. Okay, so right here, you're given a few things, okay? So it says a gas in an aerosol can has an initial pressure of 1.40 atms at 12 degrees Celsius and is heated to 35 degrees Celsius. They want to know the new pressure in millimeters of mercury, okay? So again, you're going to put down what you know. P1 equals, P2 equals, T1 equals, T2 equals. So my P1 was 1.40 atms. My first temperature reading was 12 degrees Celsius. I'm going to add 273 to that, and I get 285 Kelvin. And then my P2, you're looking for that, excuse me, and my T2 is 35 degrees Celsius. I'm going to add, again, 273 to that number, okay? And I get 308 Kelvin. Now, again, what do you have to do? You're going to solve for P2 first. Some students will want to convert the 1.40 atms to millimeters of mercury. I mean, if you want to do that, you can, but I would rather wait to the very end to do that. Okay, so you don't get all these things discombobulated. Okay, so if I were you, I would actually do that at the very end rather than converting the ATM up front to millimeters of mercury. I mean, you can do that, but I would rather wait. So now your P2, okay, your formula for P2, again, P2 equals P1 times T2 over T1, okay? So what you're going to do, again, you're going to use your formula that you know, which is P2 equals, so the first pressure reading that they gave you in the problem was 1.40 atms. 1.40 atms times T2, which is 308 Kelvin. All of that over T1, which is 285 Kelvin. Okay, so P2 equals, let's plug it in. But before we plug it in, you know, I always like to find out from you guys if you can predict the answer. Remember, if your pressure, well, hold on, not your pressure. Woo, look at that. Thank you, Lynn. Thank you, thank you, thank you. Appreciate that. I got to make sure I shout you out again. Thank you. So, you know, if your temperature increased, then your pressure is also going to increase. So it's going to go up slightly. Oh, thank you. Oh, wait, you can't see. I did it backwards. Thank you. Oh, that makes me feel good today. Honey, you just don't know. And for that, I want to say thank you. Thank you, thank you, thank you. Keep pushing, keep chugging. Don't give up. Appreciate that. as you guys will know, that your temperature is increasing slightly. So guess what? Your pressure is also going to increase slightly. Okay. So we can kind of guesstimate it's going to be a little bit like, close to 2, but not at 2. Okay. So let's see how. Let's plug these numbers in. You've got 1.40 times 308 divided by 285. And we get 1.51. Told you. Okay. 1.51 ATMs. Okay. And that's how you do it. Now, again, remember, they told you they want the answer in what? You can't forget about that part. You know how your teachers will do. They will tell you, you got to show all your work and complete the entire answer. They want your answer in millimeters of mercury. So what we're going to have to do is convert that new number, that 1.51 ATMs, to millimeters of mercury, because that's what they're asking you to do. So let's put that over here. Convert that to millimeters of mercury. And this is why I have my conversion factor. In case you forgot, here's the conversion factor right here. Okay. 1 ATM equals 760 millimeters of mercury. Again, let me write that here so you all can see it. 1 ATM equals 760 millimeters of mercury. So you know what we're going to do? We're going to take the number that we just got and convert that 1.51 ATM. So 1.51 ATMs times, remember, what are we trying to get to? Goes on top. What are we trying to get rid of? Goes on the bottom, the sign that is, or the unit, okay? 1 ATM is going to go on the bottom because that's what we're trying to get rid of. And what's going to go on the very top? 760 millimeters of mercury. So now all you have to do is multiply that 1.51 times 760, and you get 1147.6. But let me tell you, you only need 3 significant digits. Okay, this is real. Meaning, if this is on your test and you put all that in, your teacher's going to mark that wrong. You need 3 of those digits. So the 7 tells that 4 to go up to a 5. So that becomes 1150 without the decimal millimeters of mercury. So when you're doing these problems and you're trying to find your answer and you're looking in the back of your book and you're like, well, wait a minute, I didn't get that answer. I got 1147.6. You got to remember the significant digits rules. And so the answer is 1150 millimeters of mercury. Okay. And you know what? Let me see. I want to make sure I show y'all something. See right here. Okay, fine. And again, TikTok, y'all, YouTube, you can't see this, but if you're looking for the answer here for 1129B, you see that? 1150 millimeters of mercury. So again, this is the reason why I say, you want to make sure that you don't, that you have to keep the significant digits rules in place, and you don't want to not do that. Okay. So Katie, I actually have dimensional analysis with moles on my YouTube channel, as well as on my TikTok page. So if you go through, you'll find some mole conversions for that. But do you have a specific question about that? Because this is really pretty much the same process in terms of dimensional analysis in an indirect way. Okay, we'll do one more problem, 11.31, okay, 11.31. And here you've got, it says solve for the new temperature in degrees Celsius. Okay, so now we're doing the reverse. So before, we were trying to solve for pressure. Now you're solving for temperature, but they wanted in degrees Celsius. So for 11.31, we're going to do letter A. It says a sample of xenon at 25 degrees Celsius and 740 millimeters of mercury is cooled to give a pressure of 620 millimeters of mercury. They want the new temperature in degrees Celsius. Okay, so again, we're going to write out what was given. P1 equals, P2 equals, T1 equals, T2 equals. Okay, so here we are again. The first pressure reading was 740 millimeters of mercury. It cooled to a pressure of 620 millimeters of mercury. So we already know that our pressure has dropped. Here's the thing. They did give us T1, which was 25 degrees Celsius, but you're going to add 273 to that to give you 298 Kelvin, okay? And your T2 here, that's what we're looking for. So now we've got to reverse our formula to now solve for T2, okay? So again, P1 times T2 equals P2 times T1. If your teachers don't give you all four of these formulas derived out of this one base formula, okay, you should know how to get the unit that you're looking for. Because I'm looking for T2, all I need to do is just multiply P2 times T1 and divide that by P1, okay? Now, finally, okay, to finish this problem out, because I'm looking for T2, okay, which is P2 times T1 over P1, I'm going to plug in my first pressure, I'm sorry, the second pressure reading. Remember, because I was initially given 740 and it dropped to 620, we know that our temperature is also going to drop. So the number that we're going to predict will be less than 298 Kelvin or less than 25 degrees Celsius, okay? We already know that that's what the answer is going to be. So what we're going to do, okay, to solve that, P2 was 620 millimeters of mercury. So let me put that on the top. 600 millimeters of mercury, 620, excuse me. 620 millimeters of mercury times T1. T1 was 298, okay, Kelvin, over P1, okay? And P1 was 740 millimeters of mercury. So again, all we have to do is cancel out, whoops. So all we have to do is cancel out our millimeters of mercury, okay? Thank you, thank you, thank you. And now you end up with, okay, because that 4 doesn't look a 4. Plugging in our answer, okay? So 620 times 298 divided by 740, and we get 250, okay? T2 is equal to 250, because again, we only need 3 of those significant digits, okay? And we get 250. Now, we got to put the answer in degrees Celsius. So all we're going to do is subtract 273 from that number, okay? So we're going to subtract that, and let's go ahead and do that now. Okay. Whoops. Okay. So right here, because we got 250 Kelvin, we got to put our answer in degrees Celsius. So what we're going to do, okay, is subtract 273 from that, okay? So 250 was what we got in Kelvin. So remember, if we're trying to find degrees Celsius, okay, if we're trying to find Kelvin, we say degrees Celsius plus 273, right? But if we're trying to find degrees Celsius, you're going to subtract 273 from both sides, okay? 273 from both sides, and that's how you end up with degrees Celsius is equal to K minus 273. So yes, we are going to have a negative number because our Kelvin was 250 minus 273, okay? So again, let me show y'all. 250 minus 273 gives us negative 23 degrees Celsius. Okay, that's it. And let me make that a little bit bigger right there. There we go. It's equal to negative 23 degrees Celsius. Okay, negative 23 degrees Celsius. All right, guys. So that is my time today. And here's the answer right here in the book. And again, you guys can't see it on YouTube, but I'm zooming in so y'all can see that. 11.31 was negative 23 degrees Celsius. Okay. So that is my time, ladies and gentlemen. I will be back on tonight. So if you all have friends that are taking chemistry during the day, but they are free in the evening time, by all means, have them come back through. I go live Monday through Thursday, 12 noon Eastern Standard Time and 7 p.m. Eastern Standard Time. Okay. So these are my times when I go live right here in case you needed to know. Okay. Take a screenshot if you have to. Okay. But by all means, make sure that you guys keep pushing in your classes. If they're getting too tough for you, come contact me, okay? And I'll get you back on the right track, okay, guys? Thank you all so much for the love, the roses, the animated figures that were bouncing on the screen. I appreciate that. And your kindness does not go unnoticed. I really appreciate you guys. You all have a wonderful